the AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Welcome back to AI for Climate Science, everyone. My name is Philip Stier from University of Oxford. I'm hosting this series with Duncan Watson-Parris from the University of California in San Diego. And today we're really excited to have Stephan Rasp from Google Research as our speaker. To briefly introduce Stephan, he did his PhD in meteorology, so atmospheric physics at the Ludwig Maximilians University Munich, where he started to apply machine learning to a wide range of questions, parameterizations, cloud classification, and other topics. He then went on to do a postdoc at the Technical University Munich, where he started to work on benchmarking, so started on a WeatherBench. He then joined a climate startup, Climate AI, as a lead data scientist. And in 2022, he joined Google Research as a senior research scientist. I think today's topic couldn't be much more timely, and it's on the secret revolution of weather prediction by machine learning and the efforts to benchmark their performance of these models really through WeatherBench 2. So I'm really excited to listen to your talk, Stephan, and over to you.
Thank you very much for the introduction. Let me share my screen here. There you go. Hopefully you should be seeing this. Okay. I hope a lot of you are interested in what's been going on. We've had the GraphCast official announcement, so maybe that got a lot of people interested. So I'll talk today about what's been going on in the world of using AI for weather prediction in the last few years. And I'll talk a little bit about our benchmark for AI-based weather models called WeatherBench. But because benchmarks by themselves are kind of boring, I will spend most of the talk actually summarizing sort of the state of the art of where we're at with AI-based weather prediction and speculate a little bit whether we are experiencing a second revolution of weather prediction. And if we're talking about a second revolution, there obviously has to have been a first revolution. And that happened when weather forecasting changed from being a sort of scientific art where forecasters were looking at observations, were drawing weather maps to make predictions about future weather, to a numerical science. I'm showing a picture here of the ENIAC, which is one of the first supercomputers, and that supercomputer was actually used in 1950 to create one of the first numerical weather forecasts. This was experimental at the time, but it was a forecast based on the equations of physics. It took a few more years before operational weather forecasting really became a thing, but what we've seen ever since is that with increasing computing power and improvements to the models, weather forecasts have been getting better and better. And so I'll show this graph here, which is kind of a famous graph in meteorology, and it shows the evolution of forecast skill measured by the anomaly correlation. So you want to have a high anomaly correlation with the actual weather that happened 4 different forecast lead times, for different forecast horizons. Starts at around 1980, this graph, up to now. And what it shows is the accuracy or the skill of a 3-day forecast, of a 5-day forecast, a 7-day forecast, and a 10-day forecast. And you can see how these forecasts are getting better and better gradually. And so, for example, if you look at a 7-day forecast now, it's about as good as a 5-day forecast was 20 years ago, which again is about as good as a 3-day forecast 20 years before that. So we get about a forecast improvement of about 1 day per decade. Now, what you'll note, and this is why this has been sort of called the quiet revolution of numerical weather prediction, is that the improvement in forecast skill is gradual. There are some wiggles here, and these are just wiggles based on the weather that happened to happen that year. But there are no sort of sharp jumps in forecast skill. No single model improvement has ever really brought a big change in forecast skill. It's a lot of small improvements on all fronts. The one exception here, and I'll note that, is you'll see that this spread here, this blue or these shaded areas, that is the difference between forecast skill in the southern hemisphere and the northern hemisphere. And that gap became a lot smaller around 2000. That was because satellite data got a lot better and was a lot better incorporated into these models. So there we actually have a bit of a step change in forecast skill for part of the globe. So you'll note here that the timescales we're talking about here are sort of decades. Now, if you contrast that to what's been going on in the world of machine learning, we see a very different timescale. So I just grabbed a random plot here to illustrate this. This is showing the size of transformer-based models and how it's kind of exponentially increasing. But what I want to highlight is here the timescale. Here we're looking at, back at 2017 when the original transformer paper came out. In the world of machine learning, that is a very long time ago. But if we look at the world of numerical weather prediction, that is, the methods that we were using in 2017 would be very, very, very similar to the methods we're using now. So very different timescales that we're talking about. Now, back in 2017, 2018, machine learning was already kind of a big thing, or becoming a big thing. Some first successes in game playing or computer vision have been achieved in machine learning. And around that time, a lot of people in the weather and climate community started asking, well, how can we use these new advances in machine learning, deep learning, for the problems we're facing in weather and climate prediction? And if we're asking this question, we can kind of take a look at where could we apply machine learning in the process of making a weather forecast. So this is sort of the chain of processes that happen to create a weather forecast. You start out with some observations. These observations you need to somehow convert into something that a model can use as an initial condition. Models tend to like all the variables that they need on a 3-dimensional grid, but observations are often giving you either sparse observations, so weather stations, have location, you have measurements at a bunch of points, or satellites. They give you nice global coverage, but they're indirect observations. They don't directly measure temperature, wind. They just essentially take pictures of different wavelengths. So you need some process of converting the observations to what you call an analysis, an initial condition for the model. If you do this retrospectively with future data, you call it a reanalysis. And that process is typically called data assimilation. It uses a model as a prior and physical-based observation operators to create this reanalysis. Once you have this initial condition, you can start a numerical weather model. And right now, these models are traditionally based on physical principles. And if we zoom into a model, there are kind of 2 core components. The first is you need to solve the equations of fluid flow, the Navier-Stokes equations, and you call that the dynamics of the model. And typically, it's assumed that you can do so reasonably accurately at a given grid space, right? But then you have all the other messy stuff that's happening in the atmosphere. You have your clouds, your cloud droplets, you have radiation, you have turbulence. Each of these processes is way too small to be represented on a model grid, but they're really important. So you need to find some sort of approximation of the effects of these processes on the model grid. And these approximations you call parameterizations. If you bunch all the parameterizations together, often called physics, which is obviously kind of silly because everything's physics, but there we are. And these physics are really where a large part of the model error comes from in weather and climate prediction. In any case, once you have your model, you run through many, many time steps of this loop to create your raw forecast. But few people actually use the raw forecast, and that is A, because models do have errors, they have systematic errors, and you want to remove them, you want to bias correct them. Or B, the quantity that you're interested in might not actually be directly predicted by the model. So for example, if you're interested in the probability of hail or tornadoes, then that is typically not something that the model directly outputs. You need to do an additional post-processing step. Now, if we look at the sort of chain of events that is happening, and think about what machine learning or supervised learning is, the supervised learning takes one data set and sort of maps it to another data set, or learns to map it to another data set. And in principle, any of these blue boxes can be a machine learning problem. You can try to use machine learning for any of these blue boxes. Now, post-processing has been an area where machine learning has been used for decades already, mostly very simple machine learning like linear regression, model output statistics. So that's kind of a natural way. But back so in 2018, when I was doing my PhD, a lot of the early excitement of using machine learning was actually in this physics component of the models. As we talked about, this is sort of the model component that causes the largest errors in weather and climate predictions. And so it kind of makes sense to try to improve that with machine learning. The idea being that you run a much higher resolution model, a higher quality model, hopefully, to create a training data set that you then can use to train a machine learning algorithm and have a machine learning parameterization. And a few people set out to do this. You run a high resolution simulation, then the first problem is from your high resolution simulation, you need to somehow figure out for a given Corsa grid that you eventually want to use, what will be the subgrid component of that. That's not such a trivial process. But anyway, once you've done that, you train a machine learning parameterization offline on that training data, right? So offline means like not within the model. It's something you do outside of the model. And that works really well. Like offline skill of these models at reproducing the training data set, at mapping sort of the inputs and the outputs is really good typically. But then obviously what you want to do is you want to plug your machine learning model back in and couple it to the dynamics and run it through many, many time steps. And this is where the problems appear, because when you do this, when you run your machine learning parameterization online, you can imagine that the machine learning parameterization feeds back with itself. Essentially, you have a different distribution than what you've experienced during training, and oftentimes you do not get the end result you want, which is a better weather forecast or a climate prediction with better climate statistics. And sort of this large gap between what you're optimizing for, which is a single time step, and what you actually want, which is like a several day weather forecast or a long-term climate simulation, that is hard to overcome. And several teams have tried, but that approach never really fully worked. Now, to overcome this, you would somehow want to train your machine learning parameterization online. But to do this, you would need to actually learn in the system, which would mean you need to basically differentiate through the dynamics. You would need a differentiable dynamical core. Back in 2018, this was like a long way away. Actually, now, a few weeks ago, a paper was published, and I'll spend the last part of my talk covering that, which is really exciting. But, this turned out to be quite difficult. So some people were asking, well, okay, can we just completely replace the entire model and go from sort of a reanalysis state to the raw forecast? And there were a few papers that tried this. So in 2019, the 3 papers were published. You can see them on the left here. And all of these were pretty simple. They used pretty coarse resolution, and the results also weren't that exciting. I'm just showing one example here from the paper that Jonathan Bain published. And you don't need to worry about all these different colors. This is showing error with forecast time. And the best machine learning model that he trained was the red one. The important thing is this brown curve down here is a physics-based model, and the gap is really large. So this forecast is closer to the skill of a persistence forecast in a way than to the skill of a physics-based forecast. So still pretty far away, but the approach was interesting. But one problem with these three studies was that they all used a different data set. They all used a different way of evaluating the model, so they really weren't comparable among each other. And so when I saw this, I was kind of inspired by the success of benchmarks in the machine learning world. So a lot of you might know ImageNet, which kind of launched the deep learning revolution. And so I reached out to these authors, and we sat down and figured out a benchmark for data-driven weather forecasting. And that's what ended up becoming WeatherBench. WeatherBench was basically contained a pre-processed data set. It contained a evaluation protocol and code, and a leaderboard on the GitHub page. And WeatherBench was really well received, got lots of Twitter likes, a lot of GitHub stars, was cited a lot. But then after its publication in 2020, for about 2 years, not much happened. And if you look at the leaderboard of WeatherBench 1, you'll see that apart from all the baselines that were contained in the original paper, there were only 3 new studies added, one of them being my own work. And if you look at the skill, you'll note that the gap to the operational model is still really, really large. And during that time, I personally, maybe many other people also, got a little bit discouraged by the idea of purely data-driven weather forecasting. In that paper, in fact, I came to the following conclusion. I said, for the resolutions of current operational numerical weather prediction models, which is around 10 kilometers, it's unlikely that there's sufficient data to challenge these models, meaning, the operational models. And I even refer to the great Tim Palmer for a theoretical argument, and he wrote an essay in 2020 where he thinks that for medium-range predictions, he thinks it's extremely unlikely that purely data-driven approaches will be able to rival the skill of physics-based approaches. And I even tweeted this gem. I asked, can data-driven medium-range weather forecasts beat physical models? Theoretically, yes. Practically, there isn't enough data. Now, in hindsight, this obviously looks quite silly. And one of the biggest learning experiences of my career was when, about 2 years after the launch of the original WeatherBench, I got an email from somebody I'd never heard of, a guy called Ryan Kiesler. And he sent me a draft of a paper that he worked on where he used a graph neural network for exactly this purely data-driven weather forecasting. And he achieved skill that I had not thought was possible. His models were almost as good as some of the physics-based models. And that kind of taught me the lesson that, I shouldn't jump to conclusions and I shouldn't take my own assumptions too seriously. And obviously, we all kind of will probably all know that what happened afterwards. And so I kind of just plotted this evolution of forecast skill here. This is skill, so higher is better. These are sort of the initial attempts in 2019. This is the WeatherBench paper. Then there's this period of around 2 years that I was talking about where, models were still pretty bad and not much happened. And then, in early 2022, we saw sort of this Kiesler paper, which showed us that, a lot more is possible. And at the same time, a few weeks afterwards, I think ForecastNet version 1 was published, which in terms of skill wasn't quite as good, but it showed that you can really scale up these models to really, really high resolution. And obviously, we know what kind of happened afterwards. All of these, models like Pangu and GraphCast, Fengwu, Fuji, and several afterwards that I didn't include were published that were, rivaling operational models in terms of skill, something that most people didn't think was possible even, a year or two before. Now, because these new models were so far better than the models that WeatherBench 1 was designed for, they also didn't use WeatherBench. It was way too low resolution, WeatherBench 1. But a lot of the pain points that WeatherBench 1 was trying to solve still exist. So let's think about what everyone has to do that wants to train one of these, next generation weather models. The first thing is you need to download and process your training and baseline data. And those data amounts can be really, really large. Now, we all love to use ECMWF's data because the quality is just really high. But what nobody loves is downloading data from ECMWF, because it can take weeks or even months or longer for a lot of these data sets. So if everyone has to do that, that's a big redundancy. Then in terms of evaluation now actually is quite a computational challenge. A single year forecast can be tens of terabytes. It's much larger than RAM. So you need some way of being actually able to evaluate these large volumes of data. And then the third thing is like kind of what led us to create WeatherBench 1 initially, which is that, if everybody uses their own evaluation protocol, it's really hard sometimes to exactly reproduce the details of the evaluation. So you want to have an apples-to-apples comparison of different models. And so when I started at Google, it kind of became clear that we want to update WeatherBench. And so that's what we did. It's called WeatherBench 2. And WeatherBench 2 consists of 3 different components. It consists of of data, it consists of evaluation code, and it consists of an evaluation platform. And there's also a paper that describes the design principles that went into WeatherBench, and also gives you a lot of details about the metrics and so forth. So I want to take you through these 3 components now and show you what WeatherBench is. The first is data. So we have publicly available, free to use, cloud optimized data sets in the ZAR format. They're on Google Cloud Storage, and they contain a lot of the data sets that everybody wants to use. So we have a comprehensive copy of ERA 5. We have the ECMWF, IFS models, both the high resolution version and the ensemble version for baselining. And we have a bunch of other for some of the machine learning models for baselining as well. And so that means that you don't need to use Copernicus or Mars anymore to download this data, and it's immediately available. All of that data is at ERA 5.25 degree resolution, but also regridded to several low resolution if you want to work with smaller data sets. If you go to the GitHub page, you'll find a link to the documentation, and that has a data guide that shows you exactly what data and which variables and so forth we have. The next thing is the evaluation code. So that's what the GitHub repository has. And it's based on Apache Beam, which allows you to write scripts that distribute computing across many, many nodes. We use Xarray for all of our data sets, and there's an Xarray Beam package that links Apache Beam with Xarray. These can be run on the cloud. So for example, using Dataflow on Google Cloud, or probably also other cloud providers. And there's a guide on the documentation as well on how to do that. Obviously, all of the metrics that we're using for WeatherBench are included. And if you want to just check out, how it works, there's a quick start guide. It's a collab that you can run and do some quick evaluation. We also have a lot of other processing scripts for computing climatologies and so forth that might come in handy. So you can also check that out. And finally, we have an evaluation platform. So you can find it under this webpage. And it shows scorecards and interactive graphics of all the participating models. You can see all the participating models here. If you go to the website right now, it still has a much smaller set of models. That is because I'm currently in the process of updating and adding all of these models. So you get like a sneak peek of what's about to come in hopefully a few days. So what we have is a bunch of physics-based models, all coming from ECMWF at the moment. And a lot of the sort of state-of-the-art machine learning-based models, including now operational versions. We'll get to that in a little bit of Pango and GraphCast and the new NeuroGCM versions. Now, I know that there are some models that some of you might have heard of that are not included. So most notably, probably NVIDIA's ForecastNet. There's also Microsoft's ClimateX paper and also FengWu. We are working with the authors on getting those forecasts on there. So we're always very willing to help people getting forecasts on there. So if any of you have some forecasts that they want to have on WeatherBench, I'm more than happy to help. Okay, and I just want to show you like what this website looks like. So it has these interactive panels where you can exactly choose which variable, metric, region, resolution you want to look at, and then you can select or deselect these different models, and you can also zoom in and so forth and compare them if you want to compare the models relative to another model. So maybe not right now, you should be listening to this talk, but maybe eventually after this talk you can check it out. And yeah, if there's feedback, by the way, the best way to do this is to go to the GitHub page and file an issue there. I'm monitoring those, and I'm more than happy to receive feedback, or if somebody finds a bug, then please let me know. Okay. So the advertising portion of this talk is over, and now we can get back to the actually interesting stuff. And I want to basically ask the question now, how good are these machine learning models? And well, we can look at the scorecard on the WeatherBench website. Again, this is the soon to be updated version with all of the models. So we have 4 different variables here. We have lead times from 1 to 10 days. So it's the forecast horizon. And what this is showing is the RMSE for these 4 different variables of different models. So this is, you have the physics-based models here. So these are the ECMWF models. And then you have a bunch of machine learning models. Now, I'll note one thing here. What I will not do in this talk is go into the details of these models. It just isn't time, and I wanted to sort of take a bigger picture approach in this talk. Many of you might be familiar with how sort of these large-scale AI-based weather models work. But if not, maybe I'll give a sort of 1-minute brief introduction. This is very superficial, but in essence, what these models do is they take a they use a reanalysis data set, specifically ERA5, as training data. So ERA5 is a data set that for the last 40 years, now even longer, but most people use the last 40 years, every hour gives you the complete 3-dimensional state of the atmosphere. It's based on a physical model and traditional data assimilation. But these machine learning models, they learn to map from the state of the atmosphere at a particular point to the state of the atmosphere at some point in the future, typically 6 hours. Again, this varies a little bit, but roughly 6 hours. The machine learning models themselves are large, modern machine learning models. They differ in architecture. So you have GraphCast obviously being a graph neural network. A lot of these others like Pango and Fuji are transformer-based models. In any case, they're large models. And the most competitive models like Pango and GraphCast, they run at the native resolution of ERA5, which is 0.25 degrees, which is around 30 kilometers at the equator. And you train this model for the short time step. And then if you want to make a longer forecast, so 4 or 5 day forecast, you chain many of these short forecasts together, kind of like a time step in a traditional physics-based model. And that's sort of the 1-minute summary of how these models work. There's nuances, but hopefully that should capture sort of the basics. In any case, so how good are these models? Well, we'll dive into some of the model specifics later, but well, what I'm showing here is the colors are, blue means that these models are better than the ECMWF HRS model, which is typically considered sort of the best medium range weather prediction model, and red means that it's worse. And what you'll immediately see is that there's a lot of blue. You can see GraphCast, blue across the board. Here, Fuji, blue, Pangu, pretty blue, Neural GCM, which I'll talk about at the end, pretty blue. So in terms of RMSE, these models perform really, really well. What you'll also note, though, is if we look at the ECMWF ensemble, and if we look at the mean of that ensemble, that also performs really, really well against the high-resolution version. And back for the year 2020, where we're evaluating this, the ensemble actually runs at a lower resolution. So that should, in theory, be a worse model. But if you take a lot of realizations and then take the mean, you actually get a better RMSE, and that is because you're sort of hedging your bet. You're blurring out your forecast, hedging your bet in an uncertain future, and that leads to better RMSE. And so that tells us that we have to be a little bit careful to not only look at RMSE, but we have to dig a little bit deeper. And that's what I want to do for the next few slides now. So the first question that we have to answer is, well, are these machine learning models just blurring? Is that why they get good skill? So let's take a deeper look at that. Let's first look at some images. I'm going to show a bunch of evaluations now from this really great paper that ECMWF did, where they ran the Pangu model in an operational context, so initialized with operational initial conditions, not ERA5, and evaluated it using their operational framework. And you can see the Pengu model, the 2-day forecast and the 6-day forecast on the left, the IFS model, 2-day and 6-day forecast on the right. And well, what you'll note is that there is a lot more small-scale detail in the IFS model, a lot more like sort of graininess almost, which is not there in the Pengu model. So there's definitely some blurring going on. But what you'll also note is that if you go beyond this sort of small scale, there's still a lot of structure in the Pengu model, even at day 6. So it seems like the blurring is definitely happening on small scales, but the medium scales or the larger scales, there's still quite a lot of structure. So if you want to look at this a little bit more quantitatively, we can look at spectra. And you can look at, these are taken from the WeatherBench website, so you can go and check these out and play around with these whenever you want. I'm showing what spectra essentially are, is they tell you how much energy, how much variability is there on different scales. So if you look at this picture, like, it tells you like how much variability is there on large scales and how much is there on small scales. So you'll expect that there's a lot more small scale variability in the IFS model if you look at these pictures. So I'm showing the spectra in terms of wavelength here, actually, not in terms of wave number. This is the more common way of showing it, but for those of you who are familiar with spectra. And I'm showing them for temperature and specific humidity. I want to look at the specific humidity one first. Small scales over here, large scales over here. Higher numbers means more variability on those scales. And what you'll note is, if you look at the black line, that is error 5, so which we can sort of assume to be kind of the ground truth. And then we look at the green line, which is the ensemble mean. You can see that the spectra is a lot lower. So the ensemble mean obviously blurs out quite a lot. And then you have the two ML models that we have on here, which is GraphCast and Pengu. And you'll see that they definitely, especially in small scales, blur out. You can see some artifacts here for Pengu, which is probably because of the way that the transformer tiles the patches. But what you'll also note is that the blurring is kind of mostly focused on the sub 1,000 kilometer scale. And there's actually less blurring going on than the ensemble mean. You'll also note that there's a lot more blurring going on in specific humidity, a field that's a lot smaller scale than temperature, where the blurring, again, is mostly limited to the sort of a sub 1,000 kilometer scale and isn't quite as grave. Even though Pengu has quite a lot of blurring here, but mostly at small scales. Why do we care about blurring? Why is that a bad thing? Well, if a model blurs, it will never be able to predict extremes. So another thing we can do is we can actually look at how well do these models predict extremes. And this, again, comes from the ECMWF paper here on the left, and they looked at how well does the Pengu model predict temperature extremes, so extreme heat. And by the way, they also evaluated this against stations, so not only against analysis or in error 5. And I won't go into the details of this, but essentially higher means better. And it actually turns out that the Pengu model predicts extreme temperatures, extreme heat, more reliably than the IFS model. On the right, this is from the GraphCast paper. We'll get into cyclones in a little bit. But they looked at atmospheric rivers. They again looked at extreme heat. And again, for both of those, GraphCast has better scores than the IFS model. Now, what does this tell us? Are machine learning models just blurring? Well, there definitely is some blurring, but it seems to be mostly limited to small scales. It's not just emulating an ensemble mean. And that does not seem to stop machine learning models from predicting extreme weather, at least extreme temperatures. Now, if you looked at a field like precipitation, which is a lot smaller scale, the picture would be quite different. So I'm not saying that there isn't work to be done for machine learning models, but the story isn't as simple as that these are just blurring. There's definitely some structure left. Okay, so we looked at blurring. The next thing that people often say is that, oh, these models aren't operational, right? So you have in the papers or all these models are purely trained with error 5, which is this reanalysis data set, and they're also tested using error 5 as initial conditions, which is not really fair because error 5 is, again, it's a reanalysis data set. It uses observations from the future, and it's not available in real time. So if you really wanted to run this, you would have to use other initial conditions. And thankfully, people have done this now. Again, this is from the ECMWF paper, where they used the operational ECMWF initial conditions to initialize Pangu. And actually what they found here, this is the solid blue line is the HRS version, and the dotted blue line is the sort of traditional ERA 5 initialized version. They found that actually for a 2-day forecast, the operational version of Pangu is actually better, and for 6 days it's about the same. In the soon-to-be released update to WeatherBench, we also now have GraphCast operational and also Pangu operational. And I won't go into the details, but the red and the pink line you'll see are the two different GraphCast versions, and they're very close. So what kind of that tells us is that this sim to real gap, that going from sort of this reanalysis data set for training to operational initial conditions, isn't very large. Pangu was not fine-tuned. The GraphCast model was a little bit fine-tuned on the operational initial conditions. Pangu was not fine-tuned, and out of the box, it actually works really well. So that's really positive. And we now actually have operational machine learning models. ECMWF did a really awesome thing. They made these models operational using their framework, and they have live forecasts that you can check out right now. If you go to ECMWF and go to the charts page, you'll find machine learning models, different ones. So you have their own AIFS that they're developing. You have ForecastNet, the latest version, GraphCast, and there's also Pangu on there, I believe. And you can now check out, what these models predict for real weather in real time. And people actually use this during this hurricane season. We had a thankfully not super active hurricane season or a super impactful hurricane season. But there were some interesting hurricanes. For example, Hurricane Lee, which sort of traveled up the east coast of the United States and then made landfall here in the Northeast. And people on Twitter, they sort of compared how the machine learning models predicted this hurricane would develop to traditional models. And it actually turned out that for this particular case, right, it's not statistical analysis, but for this particular case, GraphCast predicted the correct landfall earlier than the other models. And this sort of kind of matches what you can see in statistical analysis of hurricane track. Again, maybe you saw it briefly, GraphCast did some analysis, but also here's the sort of independent ECMWF analysis from their paper, where both Pangu and GraphCast tend to be better on cyclone track error. Now, the one thing where these machine learning models really aren't good yet is predicting cyclone intensity. Cyclones are pretty small scale features, so that small scale blurring that we talked about is going to become really important, and that means that the cyclones are typically too weak in these machine learning models. Okay. Next thing I want to talk about is observation. So we talked about going from here to here, but what about here and what about here? Can we use observations, raw observations, both in the input and the output of the model, and can we somehow make these models better? Now, I'll speculate a little bit about the bigger picture of that, but I first want to show you sort of an example that of how this could work. And that example comes from the MetNet family of models that was developed by some colleagues of mine. So MetNet started out as a nowcasting model, so essentially predicting precipitation, and it's a regional model. So here we see it has it predicts rain over the United States. There's also a European version, and the other thing about the MetNet model is it predicts, rather than sort of a realistic picture of what weather could be like, it predicts a probability at each point. So what you're seeing here in the bottom here is sort of a probability that rain will occur. So this should not match sort of what happened in the ground truth. It predicts up to a day and shows really good scores in terms of precipitation skill. And the way it works is you have as input, you have a traditional analysis. So it takes the physics-based analysis from the US high-resolution model, HER. It takes radar imagery, obviously, if you want to do nowcasting. It also takes geostationary satellites. And in MetNet 3, they also use station observations. Now, station observations are typically quite hard to use because they are sparse, right? You have station observations at some locations, but not in between. You'd still like to make predictions for every location, not only where you have stations. So the way MetNet deals with this is what they call densification, which is essentially they put the station observations on a grid and train the model with it, only supervising where you have observations, but the model still learns to generalize to make predictions everywhere in between. And you can see some on the top here, some wind speed forecasts where you can see all these values and so forth, and it has learned that. And again, in terms of evaluation against station observations, it does really well in comparison with baselines like the HER model or the ECMWF ensemble model. So this is a regional model. It's a short-range model up to 24 hours, but it kind of shows that you can use observations. And I think that, well, the first thing I like to say is that, if we look at global models, a lot of them, they evaluate and use error 5 as sort of the ground truth. A lot of people will point out that, really you should be evaluating against observations, and I absolutely agree. What I would like to counter a little bit is this notion that evaluation against error 5 or some reanalysis data set isn't useful at all. For some things like precipitation, that might certainly be the case where error 5 is just really not a good ground truth. But for a lot of other variables like surface temperature, error 5 is still a relatively good ground truth data set. And ECMWF, for example, has made the comparison between evaluating against analysis and evaluating against stations, and the results of these new machine learning models was actually quite similar. So while I agree with this, I think it's also important to realize that there's some value in reanalysis-based evaluation. Now, if we think about this chain of processes, and if you think about data assimilation, then the holy grail would obviously be to completely get rid of any physics and the data assimilation, and to directly train a machine learning model to map from the raw observations to whatever you want to have in the end. Now, I think that while I don't think that, I don't want to make any judgment of whether this is possible or not. I think this is an open question, but I think that it's unlikely this will happen in the near future. It's simply very complex. The observations are very messy and so forth. And so I think that for now, like traditional data assimilation will be a part of the forecast chain. But I think what we will see, and what MetNet has already done in a regional context, but I think what we'll see much more in the global context is that we see an augmentation of the reanalysis data, both in the input and the output, so that the data assimilation process and the post-processing process sort of become part of the model. Not completely getting rid of traditional reanalyses, but augmenting them with really high quality data sets. Okay, and in the last part of this talk, I would like to talk a little bit and come back to this question of, can we actually just leverage what we know is good from the traditional models, which is the dynamics, and learn the part that we know is not so good, which is the physics. And we mentioned earlier that the problem was that traditional approaches, or like the first approaches, they trained offline, plugged in their learned machine learning model into the model, ran it online, and were hoping for the best. And oftentimes the best wasn't so good. You'd need a differentiable model to actually learn online, and now we have such a model. This is a paper that just came out a few weeks ago called Neural General Circulation Model, so Neural GCM for short. You already saw this on sort of the preview of the WeatherBench scorecards, and I want to dive into this a little bit and see what they did. And this is pretty much the same graph that I had earlier, just in the previous slide, but a little bit more involved. So I want you to focus sort of on this part first. This is exactly what we have here. We have a dynamical core. We have physics. In this case, is a machine learning-based physics parameterization. And then you step through this many times, through many time steps to make a forecast. They also have an encoder in the beginning and a decoder in the end, in order to map from sort of the inherent model grid to the outputs that they want on an error 5 grid and so forth. But those details are not so important. The important part is that the dynamical core is fully differentiable. It's written in JAX, and so you can use it in combination with any machine learning model. And that allows you now to make a longer forecast, like a few-day forecast, look at the error, and then back propagate, compute the gradients back through many of these time steps in order to optimize the weights of the learned physics to minimize the forecast error. They also have an ensemble version where they add some noise to the learned physics, essentially making it a stochastic parameterization, and we'll also look at that. And that model is actually optimized for ensemble scores, so not only minimizing sort of the root mean squared error, but actually minimizing the CRPS in essence. And with that and some additional tricks of making the model more realistic, they actually achieve something that a lot of other models don't do, and that means that the NeuroGCM model doesn't blur as much. This is an example of that. What's shown here is this is water vapor, specific humidity, 1 day, 5 day, 10 day forecast. I highlighted the panels that I want you to look at in red. First, this is the ECMWF high resolution model. This is obviously a physics-based model, so it's going to stay realistic throughout its entire integration. If you, for example, I know it's a little bit small, so if you have a small screen, you just have to believe me. But if you look at the intertropical convergence zone here, you see a lot of detail here, and you still see a lot of detail at 10-day forecast. Now, go over to GraphCast, right, where we definitely have some blurring. We saw this earlier. You already have some blurring at 1 day. That is also, this model is a little bit lower resolution. But then if you look at 10 days, you see that the structures are very sort of blurred out. Now, if you look at NeuroGCM, first of all, this is a coarser resolution model. So naturally, it's always going to look a little bit smoother than the sort of higher resolution, 7 times higher resolution ECMWF model. And so you have structure here. And then if you look at 10 days, you still have structure here. Actually, if you looked at the spectra, the energy on small scales would barely go down throughout this integration. That is really, really cool. So you have realistic forecasts, but also, do you also have good forecasts? Well, yes, you do. This again is from the WeatherBench webpage. Long story short, the high resolution version of NeuroGCM at 0.7 degrees is approximately as good, a little bit worse than GraphCast. But you can also run NeuroGCM in an ensemble version. You can look at the mean of that, and that mean actually is better in terms of its mean RMSE than the IFS model. And it's also better in terms of an ensemble metric called, or a probabilistic metric called the continuous rank probability score, which looks at the entire forecast distribution and evaluates the quality of that. It also outperforms the IFS ensemble there. It produces reasonably reliable ensemble. So something that people often look at is the spread skill ratio. It tells you essentially how broad is the ensemble, or how much variation does it have between the ensemble member, and that on average should match with the error that you get for your ensemble. So this ratio here, the spread skill ratio, should be around 1, and it's a little bit above that, but the scale here is very small, and so you get a reasonably reliable ensemble. One visual example here is on the right. You see this is a hurricane forecast from the ECMWF ensemble, and each of these red lines is one ensemble member, and you can see that this is sort of a plume of potential hurricanes that you'll often see when a hurricane comes up. In black is what actually happened. And here you can do the same now with a NeuroGCM ensemble, and it produces a reasonable plume. So that's really, really cool. And then one thing that's really exciting about this model too is that it can produce stable and realistic long-term simulations. So a lot of the other machine learning models like GraphCast, PanU, if you rolled them out way beyond what they're meant for, which is like the 10-15 day time scale, then eventually they would just produce garbage or crash. But this NeuroGCM model is actually long-term stable, and so that allowed them to actually run an AMIP simulation. AMIP simulation is a simulation where you run your model, you prescribe the sea surface temperatures, so you only run an atmospheric model, and then you see how your atmospheric model sort of reacts to the changes in sea surface temperatures. And this is a simulation from 1980 to 2022. And with the prescribed sea surface temperatures, This is global mean temperature. The NeuralGCM model is able to sort of reproduce the variations in global temperature really well. Error 5 is here in orange, so that's sort of your ground truth again. The blue is an ensemble of NeuralGCM simulations, and there's an AMIP comparison. So this is what it is, like atmospheric model intercomparison project, similar to CMIP, but just for atmospheric models. If you look at the mean of all the AMIP models, the traditional physics-based models, they're actually further away from the error 5 mean. This is just obviously looking at global mean, but you can actually also look at, for example, what they've done here is looked at the distribution of tropical cyclones during a year of those simulations. Above here is the error 5 sort of ground truth, and down here NeuralGCM. So these cyclones shouldn't match one-to-one. It's just about the statistical sort of distribution. Down here is an example from a traditional physics-based model that in this case does a lot worse than the NeuralGCM model. So it's really exciting because we can now run really long-term simulation with a machine learning. This is a hybrid model, like a machine learning physics model that does really well and does so at relatively close resolution, right? This is 2.8 degrees. It's a 300-kilometer scale, really coarse, but so it allows us to run really fast simulations, but they're also still reasonably accurate, which is obviously one of the big advantages of machine learning. I didn't mention it explicitly in this talk, but one of the advantages of machine learning is not only that they're potentially better, but that they're much faster during inference time. Like when you actually want to run a forecast, you can run a GraphCaster, whatever NeuralGCM forecast in a few minutes at max, versus and that is on a single GPU or TPU versus hours on a supercomputer like the ECMWF models. Okay, so pretty exciting developments. And let's now come back to the question that I asked initially, and that is, are we experiencing a second revolution of numerical weather prediction? And to put it into context, I grabbed this graphic from ECMWF that is pretty similar to the quiet revolution graph that we saw in the beginning. It's just showing it a little bit differently, so let me walk you through this. What this is showing is the time at which a forecast drops below a certain level of skill. So again, this is the anomaly correlation here, and the red line, for example, is showing the forecast horizon at which the ECMWF model drops below 90% anomaly correlation. So obviously you want this to be as late as possible. So if you go up, that means that the forecasts are improving, which is what we saw earlier too. So right now, this is happening at around 4.5 days, and it's showing it for a bunch of other thresholds as well. I also plotted GraphCast as sort of an example of these machine learning models. But as we've seen earlier, a lot of these machine learning models have pretty similar skills. So a lot of other models will probably look quite similar. I plotted this for the year 2020, which is the year that we do most of our WeatherBench evaluation at the moment. And you can see that the gain over ECMWF in this one metric is about half a day. And earlier we said that, we have this sort of improvement of skill of about 1 day of forecast, one forecast day per decade of real time. And so that would mean about 5 years of progress. Actually, if you look at this graph, it might be even a little bit longer. So 5 to 10 years of progress all at once. Now, again, this is just showing this one metric, and you have to be a lot more nuanced, obviously. But I think what I wanted to demonstrate in this talk is that while these models certainly aren't like the solution to all of our problems, they also hold up to a lot of additional evaluation. So there's actual skill there. It's not just that they're sort of optimizing for this metric alone. What's also important to consider here is that this is sort of the first generation of really large-scale AI-based models, right? Like we've sort of noodled around a little bit during the WeatherBench 1 times, but all these models were sort of really coarse resolution, and only in like 2022, within the last year, essentially, I think GraphCast was actually published just before Christmas last year. Now, have we seen sort of these really large-scale models? And now there's work going on sort of the second generation of models. So even the first generation of models, without any like super optimization, we've seen this jump in forecast skill. Now, let's get now to sort of the big questions. And I think the first big question is, where's the ceiling for these machine learning-based models? The question, if we look at this graph again, is, okay, we have this jump in forecast skill now, but what's going to happen afterwards? Are we just going to see the same slope here of improvement, but shifted upwards a little bit? Or are we going to see a steeper slope? Now, I don't have the answer for that, and I think it'll be really exciting to find out. But I think one sort of one interesting fact is that this first generation of models, they were in a way kind of all developed independently. They use quite different architectures in some cases, and yet they produce pretty similar forecast skill. There are obviously some variations, like a few percent here or there, but what does this sort of tell us? Now, the commonality between these models is that they all use the exact same training data set. They use error 5. And does this tell us that the training data set puts an inherent limit on how good these models can be? Well, I don't know that, but if that is the case, then the question does become, how far can we go beyond these beyond physics-based reanalysis? How well can we incorporate additional observations into our system to sort of make these forecasts better? And I think this will be really interesting to see, and I'm really excited to see what models we'll see next year and what the rate of improvement will be. In terms of evaluation, I think the big question is, well, what about these sort of really extreme events, right? Like, so we've seen some extreme event evaluation or extreme heat and so forth, and that's great. And we should definitely aim to statistically evaluate what we can. But, you know, the really, really extreme events, the sort of 1 in 100-year events, they're so rare that you can't necessarily statistically evaluate them. And here the question obviously is, can AI-based methods that might have never seen such an event in their training data set, or even an event that comes close, right? Think about maybe the Pacific Northwest heat wave that happened a few years ago. Can AI-based methods still do well there? I don't think that we have any indications that they can't right now, but obviously we also don't know for sure that they can. And as I already mentioned, these will be really hard to statistically evaluate. And that's why it's really important that we now have these models operational live. And we can actually look at real impactful weather as it develops and look at the forecast and see if they're useful. This will be anecdotal evidence, but still it will be really, really important to see whether these models are useful. Now, in this talk, I purely focused on sort of the medium range. We looked a little bit at nowcasting with the MetNet model. I think it's pretty clear that for nowcasting, these things work. And it turns out now that for the medium range, so the 10 to 15-day time range, machine learning really works. But how far can we extend this? Can we go into the sub-seasonal, sort of 2 to 6 week time frame? Can we go into the seasonal, right, up to 6 months or even a year time scale? And this has traditionally been an area where skill is hard to come by. Machine learning methods have not made the same sort of progress there. There are some like blending and post-processing models that, you know, improved skill a tiny little bit, but nothing substantial. And I think it'll be really interesting to see these sort of autoregressive models that learn to predict for short time scales, but then unroll for longer time scales and still work reasonably well. Well, how well does it work? How far can we push this boundary? I don't know the answer. You might have to add processes like the ocean and the land, but this will be really, really interesting to try out. And then in the last minute, let me briefly talk about climate. I did not talk about climate except for showing these like AMIP simulations with neural GCM. Climate is a completely different beast, really. I personally prefer to work on weather for 2 reasons. First, the weather is a much clearer problem. It's pretty easy to define what a better forecast is, and you kind of know what you're aiming for. And the second reason is that, well, we're at a time now where I do think we're kind of looking at a second revolution in weather forecasting, and there's real potential for serious progress in the next few years. In climate, on the other hand, the question is it's a lot more diffuse. First of all, climate isn't one problem; it's a bunch of problems, and so you have the sort of big climate projections, like given a particular emission scenario, what will happen in the next 100 years? And here, it's essentially an out-of-sample problem. It's the quintessential out-of-sample problem, and using machine learning there, will be kind of difficult, probably. There are a lot of other sub-problems in climate, like downscaling, maybe ensemble generation. You now have these really high-resolution climate simulations that are being developed, but they might be so expensive that you can only run one realization. Can you use a machine learning model trained on this one realization to create more realization that allows you to estimate the probability of extreme events? I think something like this could be really impactful. But yeah, I think that still remains to be seen. I think we have to find these like killer applications in climate, whether it's a lot more clear where we are. Okay, exactly 1 hour in. I would like to thank everyone for listening. Really looking forward to the discussion, and bring it on. Thank you.
Fantastic. Thank you, Stephan. That was a really great overview of what is a very quickly moving and fast growing field. So much appreciate that. We have a few questions coming in. I have a whole host of my own as well. But I'll go to the audience first. So Michael Spicer has a question on the chat. Thanks for the interesting presentation. Can you comment on how uncertainty is handled in WeatherBench 2? So this was something I wondered as well. So can a model predict a range, a distribution, or is it based on point predictions?
Yeah, so I didn't cover this that much. So most of the machine learning methods so far are deterministic models, right? Like GraphCast and Pango and so forth. So they do not by design capture uncertainty. WeatherBench does have a range of probabilistic metrics. So I did show some of them for NeurGCM. I didn't spend too much time on it because NeurGCM right now is sort of the only model that we have on there that produces ensemble scores. So we have ensemble metrics like the CRPS, we have spread skill ratios, and hopefully we'll see a lot more ensemble models in the future, and then we might add more scores that look at uncertainty, like rank histograms and so forth. So I think that the basic sort of probabilistic scores are there. There just aren't a lot of models on there yet.
And the HRES ensemble is the baseline there, presumably.
Exactly.
Right. Okay. I had a related question actually. So I mean, one of the challenges that I know DeepMind faced when they developed their nowcasting model with the Met Office was getting forecasters to believe it and to trust it and to use it in the forecasts, and that kind of human element is something that's a little less tangible, I guess. How have these been received? I know ECMWF seems to be kind of embracing these models, or at least exploring them. What, I guess, if you don't generate an ensemble, how does a forecaster choose which one they feel are the right ones or the best ones, and how do you communicate with the forecasters to help them in those decisions?
Yeah, I mean, I think this is an open question. This is a very new field. And ECMWF has done like this first step of actually putting the live forecasts on there, which is great. And I think that that is really important. I don't have a concrete answer to your questions, but I think that getting those models in front of people that actually use forecasts to make decisions is going to be really key in figuring out, well, first of all, end users figuring out, are these models actually any good? Do we want to use them? And then also in figuring out how do we want to present these models to the general public or to end users? And I think obviously there will be a different answer for ECMWF and for Google, so I can't speak for everyone, but so I think that we're at the point now where we really need to get end users get their hands on those models and to figure this sort of stuff out.
Yeah, no, that makes sense. I mean, and practically, so I was excited to see that these models are being initialized on kind of real initial conditions. Presumably I don't know exactly how those are created in ECMWF, but presumably they run 4D-var and they get those from the IFS kind of nudge to the observations, to the latest observations. Is there a disconnect? You talked a little bit about different models and different physical models to train on. Is there a disconnect between, where those initial conditions come from and how you project forward? Is there room for improvement there, perhaps in the DA?
There's probably definitely room for improvement. Even though DA is a very, obviously you could use one of those models within 40WAR, right? Like,
right, yeah, exactly. Yeah,
you could, right? Yeah. Maybe you probably couldn't right now because you probably, like these models still produce a subset of all the variables and so forth and the vertical levels. But in theory, you could. So that's an interesting avenue for research. But I guess the kind of point that I wanted to make is that, like the distribution shift from going from sort of reanalysis, error 5 reanalysis to the operational initial conditions doesn't seem to be that large. Now, would this also be the case if you jumped from the IFS initial conditions to the GFS initial conditions? I don't know. Nobody's tried it out yet. So I don't know how robust these things are. But I think that the first signs are encouraging. It doesn't seem to be the case that small details, small differences will actually make the model really, really bad. And there was this really interesting paper from actually my PhD supervisors, but no, I was not involved, where they looked at error growth in these models. It's not realistic. Right, small errors.
I like the butterfly.
Exactly,
one.
small differences in initial conditions make absolutely zero difference to the forecast. In this case of Pengu, which kind of tells you that these models are in a way robust to input perturbations, which isn't good from a realistic forecast error growth perspective, but it's good from a reliability perspective when you change like the inputs a little bit.
Sure, yeah, and there's all sorts of interesting things around the accuracy and the precision of which you calculate these things anyway on the GPUs. But okay, all right. Yeah. Well, we have plenty of questions coming in now from the audience, which is fantastic. Philip, do you want to pick up one of these or?
Yeah, actually, I want to sneak in one myself, and then I'll hand to the audience. I mean, you basically, when you discuss sort of blurring, you said, well, would be much harder with precipitation. So let's not do that. But I kind of want to challenge you a little bit on that, because that's exactly what we want to get right to some degree. Yeah. And a slightly related question to that is true. So we want to get the granularity of precipitation right. And a second sort of tag-on question to that is, as we train on models that are not necessarily good in doing precipitation because they have parameterized convection, and therefore we know the diurnal cycle is bad and so on, are we inherently biasing us then to doing it particularly bad? And obviously, the next question would be kilometer scale models, but that's a big question.
Okay. Let me get to the second question that you asked first about the ground truth data set, right? Obviously, whatever method we choose, like we can only be as good as the ground truth. Error 5 is not a particularly good ground truth for precipitation. There, I think we have to look at more direct observations, be it maybe a sort of satellite-derived precipitation product like iMerge, which has its own drawbacks, but is probably better than Error 5 in some aspects, or be it even like regional radar or something. So we definitely need to do some work in figuring out what the ground truth data set is. Back to your first part of your question, the reason why I didn't mention precipitation all that much and why I didn't actually focus on ensembles that much is not because I think that these models already do so well on all this stuff. Like precipitation, GraphCast has precipitation, but it's not that good. Even though the operational version is actually a lot better for some reasons. But the reason why I didn't talk about this much is because I think it's a solvable problem, right? Like the first generation of these models aren't good, but I do believe that this will become rapidly better. Generative modeling exists, and I think that obviously the obvious thing is, can we use generative machine learning methods for creating realistic ensembles? And I think that the answer is most likely yes. So I would expect that within the next year, we will see models that produce realistic small-scale weather. And so I think that, while the current version of models doesn't do it, I think we will see that. If we get the ground truth right, which is also a challenge, but yeah.
So George's, I'm going to murder this surname, but George's Fragakaldis makes a really interesting related point, actually. So I hadn't thought of this. ECMWF provide the European global medium range weather forecast, and many local and national forecasting centers use those as boundary conditions for their own higher resolution local simulations. Does the blurring matter less in that case if you just want to use these as kind of boundary conditions to drive your own regional high resolution forecasts?
Oh, good question. I don't know the answer to that. I think, yeah, using an ML model as a boundary condition for a physical high resolution model, yeah, that somebody should try it out, maybe. Well, I honestly don't know. Again, what I will say though is that you could imagine using another ML model to sort of downscale and kind of replace the regional high-res model. Maybe a generative model, maybe a MetNet style model. And I think that, again, this is something that is really exciting. Obviously in the end, we want to train everything end to end, but like you could imagine a similar setup than what we have right now, a global ML model, and then a model that sort of downscales to high resolution precipitation or other variables. And I think that's a very promising avenue that people will try.
I mean, the related question a little bit from Fran Bartolage is sort of first saying that the neural GCM paper is really impressive. And then the question is really, do you think that the hybrid physics ML approach presented in that paper, or in general a hybrid approach, is it necessarily better than a pure ML approach? I think that's a question that many people are wondering. Yeah. Is the physics really redundant?
Obviously, in theory, it should be better, right? Obviously, in theory, it should be better to use physics, especially the part of the physics that you can handle reasonably well. I think the other argument is an end-to-end machine learning system is a lot less complex and a lot easier and more scalable to train. And I think that's sort of the counter argument to the hybrid approach. It's a lot harder to train and optimize these hybrid approaches compared to a pure ML model, where you can leverage a lot of the stuff that's going on, for example, in large language models, right? Like these transformer-based papers. I mean, transformers weren't invented for weather forecasting, right? So you can it's basically just using what everybody else is using now in language and vision for weather forecasting. So it's a lot more scalable than maybe a hybrid approach. That being said, there are different strengths, right? Like this hybrid approach allows you to run really long simulations that are realistic. We're not there yet with pure ML approaches, and will we ever get there? I don't know. It's an open question. So I think there are pros and cons to either, and it probably depends exactly on the application area, right? Like if you look at nowcasting, you probably don't want to run a hybrid approach. You probably just want to run a pure machine learning method. But if you look at climate simulation, then it's the other case. And so it's probably a spectrum.
Thanks.
There's a question from Shashi, actually. It is kind of I wondered as well. So you mentioned ForecastNet as having this nice property of being able to it has a slightly different architecture to many of these other models, right? Based on these Fourier neural GCM Fourier operators. Are you in contact with the NVIDIA people? Are they engaged with the benchmarking process? Do you have a feel for where
we're working on it? I think they're public. I don't know, but hopefully we'll have them on there soon. Yeah.
Okay. Okay. Cool. No, that'd be nice. It'd be nice to kind of round off that.
Yeah. There's also one paper that I didn't mention at all. There's this spherical CNN, which is also published by some colleagues of mine. It uses, as the name says, CNNs on the sphere, which again is kind of a more physics-based approach. It's low resolution, so the scores aren't quite as good, but given that low resolution, the scores are actually quite good. So that's right. Sort of maybe a similar approach to the Fourier approach. So there's certainly room for architecture improvements. So it'll be interesting to see where we'll end up.
Yeah, and actually, I mean, these simpler architectures in some respects, right? The spherical CNN, particularly when you run at a slightly coarser resolution, presumably are much cheaper both to train and to roll out at inference.
Compared to what? Do you mean?
Compared to the GraphCast or neural GCM, for example.
I don't. I honestly don't know. I would have that's something I would have to look up. I think that, like, for example, like some things are really easy to parallelize on a TPU or GPU versus other things might not be. So it's a little bit hard to say without going into the details.
But that's actually okay. That's interesting. So I mean, I guess all of these models are way faster than, you know, the Fortran code that we previously used, orders of magnitude, presumably. But maybe it reaches a point where actually, you know, the relevant benchmark in terms of compute speed is the other AI models, and you know, not everyone has a bank of TPUs they can use to run them. And
yeah, certainly. Also, you know, you could imagine, like, we were seeing this with large language models right now, that you have like sort of smaller language models that have a range of applications and are maybe much easier to fine tune or something. So we might see something similar. Yeah, it's really just like right now it's kind of the Wild West out there, and nobody kind of knows what to do with this. So it'll be really interesting to see how these are adopted in the next few years, and whether we'll see like a lot of like open source development in those, or whether not, I don't know. So yeah, it'll be really cool to see.
Absolutely. No, yeah, absolutely. I think we're heading to the end of our session. Unfortunately, there's still lots of great questions coming in. I just want to respect your time, and I know other people have places to go. But thanks again for the talk. It's been really fascinating. There's lots of exciting developments, and I think, yeah, it's been fun to observe the development of this, and I think, you know, you're humble in you know, reflecting on those maybe slightly pessimistic statements that you made before, and it's exciting. It's exciting to see where it's going.
Yeah.
And
well, thank you.
I have to get Tim Palmer's comment on the.
Oh no, it's all good.
But no, this is great. Thanks for the time, Stephan. It's been a pleasure having you, and thanks again for the talk. So just before we wrap up, I would just like to advertise the next talk in a series, which is Climate Causality by Marlene Kretschmer, discussing connecting data and theory to understand the drivers of regional climate extremes. I don't actually have the date for that off the top of my head. I think it might be in 2 weeks. Otherwise, it might be in January. But you can check out the website, our stream, and you can register for that there. So with that, I'll leave it there and see you next time. Thanks, Stephan.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.